Good afternoon, everyone. My name is Beishan Wang, and I'm presenting our work on constructing an ontology-compliant soil health knowledge graph using large language models. The title, Make Soil Healthy Again, reflects our goal not just to study soil health, but to make soil health knowledge more accessible and reusable through semantic web technologies. I only have 8 minutes, so let's skip why soil health and soil science are important topics, which they really are. But more importantly, soil science has not yet widely adopted semantic web techniques as its primary paradigm for knowledge representation. Most existing soil ontologies focusing on data annotation rather than capturing domain knowledge. Meanwhile, there are no widely accepted soil theories. As a result, knowledge remains fragmented and difficult to reuse. Our work addresses this gap with two main contributions. First, an expert-validated ontology-compliant soil health knowledge graph, and secondly, a reusable human-in-the-loop pipeline for constructing it. Here is our KG construction pipeline, which has four main stages. First, knowledge source preprocessing. We select two EEOSO reports as our primary sources. We extracted 105 paragraphs from them, like this example, containing key concepts, their definitions, relationships, and quantitative information. Moreover, one of these knowledge sources also provided a concept model for our knowledge graph. We already advised this concept model to form high-level structure of our KG. Let's go back to the pipeline and walk through the KG construction process with this example. We start with a paragraph defining soil. The LLM generated candidate RDF triples in turtle syntax, aiming to capture the concepts, the definition, relationship between each other, and the bibliographic source. After the initial extraction, we perform literal re-extraction, checking if tags stored in the definition still contain entities and relationships that haven't been exhaustively extracted. In this case, we invoke the LLM again for secondary extraction. Before post-processing, we also check their turtle syntax. In post-processing, we align with established ontologies. Here, replacing a custom predicate is composed of with argument ontology property. We then integrate triples from all 105 paragraphs into a unified graph. This raw graph typically contains duplicate entities and potential conflicting relationships. So we perform entity normalization using text embeddings to cluster similar concepts and relation disambiguation to resolve conflicts, both revealed by domain expert. Finally, in enrichment, we add invertible relationships explicitly to the KG. For example, we have soil has broader biomaterials, then we add biomaterials has narrower soil. We also interlink to external vocabularies, matching soil to argovoc and the biomaterials to null thesaurus using scores mapping properties. Finally, for validation, we define 105 competency questions, one for each source paragraph, before construction began. For example, we have a CQ, what are the components of soil from this paragraph? Each CQ is translated to a Spark query. We execute it against the KG, and the results are compared against expected answers from the source text, which achieved a semantic textual similarity score of nearly 0.9, confirming the KG accurately modeled the source knowledge. All outputs were reviewed by soil scientists for scientific accuracy. One more thing I'd like to emphasize is our use of blank nodes for complex statements that simple triples cannot capture. Consider this sentence: soil nutrient status affect biomass production in natural soils and crop yields in agricultural soils. A simple triple will lose the contextual distinction. Using blank nodes, we preserve that nutrient status affect biomass production specifically in natural soil and crop yields specifically in agricultural soil. Similarly, for indicator threshold, when the literature states different critical stock ranges for different soil types, blank nodes allow us to attach both the soil type's context and the percentage value to each range. This replication pattern is essential for accurately modeling scientific knowledge where conditions matter. Our first application is that the KG serves as a semantic backbone for the soil-wise data and the knowledge hub. Through keyword matching, each concept in our KG links to the metadata records from platforms like Cordis and OpenAir. This transforms the portal into a knowledge discovery tool. Researchers can find both standardized vocabulary terms and related scientific outputs and datasets in a single interface. Our second application is that the text to RDF mappings serve as the benchmark for the text to KG task. Unlike existing benchmarks that focus on simple triple extraction from, for example, Wikipedia, our dataset comes from scientific literature with heavy use of blank notes from conditional knowledge, making it particularly challenging. Here is some basic information about the dataset. You can see this paragraph level dataset with an average of 140 words with 92 triples per paragraph. We also run some preliminary experiments with GPT-5 in zero-shot prompting single attempt. You can see the graph burst score F1 of 0.86 shows semantic content is largely captured, but the relatively low G-Roche and G-Blue indicate the model struggles with exact structural reproduction, especially the blank note patterns. Finally, takeaway messages. First, soil science is a very important topic, but has not yet widely adopted semantic web techniques, so there's quite space to further explore. Secondly, our Soil Health Knowledge Graph provides an expert-validated knowledge representation with potential to integrate with existing data-centric ontologies into a unified framework. Finally, even LLMs can significantly reduce manual labor in KG construction tasks, especially from unstructured text, but they remain difficult to deploy directly. Therefore, a semi-automatic human-in-the-loop pipeline remains the most feasible solution at present. Thank you very much for your attention. The knowledge graph, ontology, and the source code are all open sourced on GitHub. I'm very happy to take any questions. You can also reach me at the email shown on screen. That's all from my side. Thank you very much.